In our last video, we started talking about the concept of planar kinematics, and we said that there are three types that we're going to encounter in this class. And so we've already talked about the first one, which was translation, and this video we'll be talking about our second one that we'll come across, which is rotation about a fixed axis. So to look at it, let's kind of draw like a little, I don't know, this is some body. It's just a potato-y kind of body that is going to be rotating about its axis, like a centroidal axis. You can also think of this as maybe like a rod or something. It doesn't have to be an arbitrary potato shape. It's just any body that may be rotating about an axis. And I'm actually going to bring this down a little bit here. Alright, so it's rotating about this axis, and if I take a little disc, from our body here that we're kind of rotating around to kind of see what's going on with our particles, with our body, how this is moving, I'm going to have this disc that's rotating about the origin. Right? It's going to be rotating about our center here, our centroid. And we're going to be looking at some point P that's on the outer edge of our disc, right? This is the thing that is rotating. Right, that point P is moving around and around this body as it spins around this central axis, right, this fixed axis in its center here. So what we're kind of doing is looking at the motion of point P as it goes around this central axis, right, this central axis about O. So what we have here when we're looking at this rotational motion about our fixed axis, the way that we're going to want to analyze it is using angular motion. We're going to use angular motion to analyze rotation about a fixed axis problems. So we're going to use our angular motion. And we may remember from physics our angular motion we had seen before as like our angular position, angular velocity, angular acceleration, and we've got some special symbols for those. So our angular position is going to be defined by theta. So this theta is going to be if I have some radius of this disk from O to P, some radius there, as this disk is turning, it's going to be turning by some amount. Let me move that R here. Rotating here through some angle theta. So theta gives us the position of where P is on the disk, and this change where it rotates through this point P here, that's going to be our d theta, and we call that our angular displacement. Our angular displacement is going to be how theta is changing. So this is d theta. So theta is the location of where point P is, and then d theta is how that's changing as this disk or body or whatever this is rotating around its fixed axis. We've got our angular position, we have angular displacement, and both of these are in radians. Right, it's really, really important to distinguish. These are both, all of these angles, theta and d theta, are both in radians. And occasionally you might be given these in revolutions, like how many full turns does something make. So to convert between our full turns, our revolutions, and our radians is going to be 1 revolution is 2 pi radians, right? 2 pi being the full circle in radians gives you that 1 revolution. So then along with this angular position and angular displacement, logically it goes along, we would have angular velocity and angular acceleration, right? Kind of like we've seen in our, in our class before, where we've got position, velocity, acceleration. We're going to relate them all together. Our angular ones are going to relate together just the same way. So our angular velocity, that's the velocity of that point P as it spins around the edge of that disk there, is represented by the Greek letter omega. Omega. Looks kind of like a fancy W, just an extra curvy W. And just like our linear position was, we could take the derivative with respect to time of our linear position. We can do the same for our angular position to get our angular velocity. So if I take the derivative of angular position with respect to time, that gives me omega. That gives me my angular velocity. And then finally, we're also going to have, in the same direction typically as our angular velocity, we're going to have angular acceleration alpha. So the Greek letter alpha represents our angular acceleration. And that's that rotation alpha, and much like our velocity, we could take a derivative with respect to time and get acceleration. Works exactly the same for our angular ones. So if I take d omega dt, taking the derivative of our angular velocity with respect to time, I get angular acceleration, Greek letter alpha. Or alternatively, I could take a second derivative of that angular position. So second derivative of theta with respect to time, I can get my angular acceleration that way too. Now note that these also have radians in their units, right? Your angular velocity is going to have units of radians per second, and your angular acceleration is going to be in radians per second squared. Okay, so bearing in mind that that's a really good indicator of when we have angular velocities, accelerations, positions versus just our linear ones, because our linear ones are going to be in things like feet, meters, things like that, whereas our angular one is always going to be subjected to that angle of theta that is in radians. And so lastly, since all of these relationships have been extremely similar to what we've seen with our linear kinematics, it holds true that we can also use our relationship alpha times d theta equals omega times d omega. Right? We use this ADS equals VdV, this shortcut equation, for our linear kinematics, and we can do the same with our angular kinematics. Right? It's the same concept, just applied to our to an angle, to a rotation about a fixed axis instead of a linear motion. So knowing that, with this idea that these relationships really maintain the same, what would it look like if our angular acceleration was constant? And you're exactly right. It is just the kinematic equations for constant acceleration, just with our angular velocities and accelerations and positions instead. Let's write those out. So, whoops. So what if angular acceleration is constant? Then by these same rules, by this same token, we could have that as we had v equals v naught plus at. Here we're going to have omega, that's our angular velocity, equals initial angular velocity, omega naught, plus alpha times t, right? That constant angular acceleration alpha times time. Holds true for our thetas as well. Theta, our angular position, equals our initial angular position, theta naught, plus initial angular velocity times t, plus 1/2 alpha t squared. 1/2 times angular acceleration times t squared. And then finally, we're going to have our angular velocity squared equals our initial angular velocity squared, plus 2 times alpha times theta minus theta naught. Right, so that difference in that angular position times angular acceleration times 2 plus that initial angular velocity squared equals our angular velocity squared. So they're just the same. They are the same equations, just applied with our angular concepts instead of our linear concepts. Those relationships all hold true still. So I think that makes the big question here, how do we relate those linear positions and velocities and accelerations to these angular velocities, positions, accelerations? How do those two things relate together? How can we convert between one and another? So let's go ahead and take a look at our little diagram that we had up here again. How are we going to relate our linear displacement with that angular position displacement? And it might seem intuitive to you, it might not, but what we're going to do is use our arc length equation to relate those together. Right, so we have our displacement along the arc length here. Let me do it in this red, whoops. This, we have ds, the displacement along that arc length. We can represent that with ds equals r times d theta. Right, if we have a changing ds, we have a changing d theta, we can integrate those to get that relationship between our displacement s, that radius r being either the radius of the disk or the position vector from O to P. You can think about it either way. But that r times d theta. So we can use that to relate our linear displacement with our angular displacement. Then we have our velocities. Right, and if we remember back to our curvilinear motion and our velocities, thinking about how this point P is moving, let me use a good color, maybe green. How this point P is moving is that our velocity is always tangent to the curve, right? That velocity is going to be perpendicular to that radius there, perpendicular to the way that our like that line O to P, that radius there, for our velocity. And the way that we can relate our linear velocity, that v, that tangential velocity there, with our angular velocity is that our velocity v is going to be omega, the angular velocity, times r. We can also think about it coming from the vectors as a cross product, where if we have any arbitrary vector on our axis, call that RP, that's a position vector from any point. Could be any point along this axis. Oops, RP. From the axis to point P, we can treat it as a cross product. So you might also see it in this vector form. V is the vector omega, a vector form of angular velocity, cross product with RP. You might see it this way, but more commonly we can just use our scalar value. V is angular velocity times r. And then by that same thread, if we think about our accelerations and the different accelerations we have, remember that around this disk we're kind of moving in a curve, right? This rotation is acting like curvilinear motion. So with this curvilinear motion, we're going to have, I've got a good colors for this, we're going to have acceleration in the tangential direction and acceleration towards the center in that normal direction. So here's acceleration in the normal direction, acceleration in the tangential direction to give us some overall acceleration value. So our relationships for each of these is going to be that our tangential acceleration is our angular acceleration times r, and our normal acceleration is going to be omega squared times r. And that, of course, is being derived from our an is v squared over r. And then if we substitute in this relationship, v equals omega times r, we can find that that normal acceleration relationship is holding true from this equation here. So with those, and then of course we can also still find the magnitude of that overall acceleration in the exact same way. Square root of the squares of our normal and tangential, since our acceleration vector is still at plus an for those vector forms. So that still holds true as well. So now we have this slew of relationships, right? We have the angular position, velocity, acceleration, those relationships as we see them in kinematics, as we saw them in chapter 12, now applied in an angular fashion, combined with the fact that we can convert between our angular velocity, acceleration, position, and our angular position, velocity, acceleration, all of those, we can convert between them. So we can find all of these relationships between our kinematics that we've been working with and these angular kinematics that we are going to want to work with when we have something rotating about a fixed axis. So we're going to go ahead and look at, we're going to take a look at some example problems. The thing to keep in mind with this one more than anything is that since we're rotating about a fixed axis, you want to establish your positive sense of rotational direction. And typically this is counterclockwise, but it doesn't have to be, right? You get to choose if you want it to be counterclockwise or clockwise, but those are pretty much your two options, right? You've only got you pick one for your positive, write out all your known values, and then see if you can use these relationships to solve problems. So let's go ahead and take a look at a couple of examples. All right, so let's take a look at this first example where we have a cord. There's this brown cord here that is wrapped around this orange wheel, which is initially at rest when theta equals 0. If a force is applied, as we see down here, if a force is applied to the cord and gives it an acceleration of a equals 4t meters per second squared, where t is in seconds, determine the angular velocity of the wheel and the angular position of line OP as a function of time. Okay, so let's like digest everything that they gave us there. So we have this cord that's attached to the wheel, which is causing the wheel to spin. So we can see this little indication that this is going to be spinning. We see P was probably initially here and then is moving through this rotation as F pulls this cord down. So initially the wheel is at rest when theta equals 0. I'm going to go ahead and just pull out some important information that may be helpful to me. So initially my theta initial is 0, and initially at rest indicates that I have no initial angular velocity either. Right? Angular velocity initial is 0. Then it tells me I've got an acceleration of a equals 4t meters per second squared. And there's a couple of important indications in that acceleration. So one is that it doesn't say angular acceleration, it just says acceleration. So it is just giving a, right? Just acceleration, not angular acceleration, not alpha. It does not say alpha, it gives just a. Two is that we can also tell that because it says meters per second squared and not radians per second squared. That's another good indication that that is just acceleration a, not angular acceleration alpha. And lastly, we're kind of indicated on this diagram that a is going down, right? The force applied gives it this acceleration. So because this force is being applied downwards, this acceleration is constantly just going downwards. So that force is causing that acceleration that is just the tangential acceleration. It is not the normal acceleration. This is just tangential. It does not include the normal. So a tangential is 4 times t, 4 times time. And we want to find the angular velocity of the wheel and angular position of the wheel, or angular position of line OP as a function of time. So what that's asking for is angular position as a function of time. And our angular velocity, did I say angular position? Angular position as a function of time, and angular velocity, that's our omega, angular velocity as a function of time. Both of those won't be just like answers, they'll be in terms of t. And then let's see, did they give us anything else? Not explicitly stated in the problem statement, but if we look at our diagram, we do see that this wheel has a radius of 0.2 meters. So I'm going to mark that down in my givens just because it may come in handy. We may want it as we work through this problem. So we're given a tangential acceleration. We're trying to find angular velocity and angular position. So the first thing that we're going to want to do is, one, make sure that we know what our positive direction is. Establish a positive sense of direction of rotation. So we're going to just say this way that it's rotating, that's going to be our positive direction. And we're going to use that along with all of this information that we've been given to go ahead and solve for these angular velocity and angular position. But to get there, we're probably going to need our angular acceleration, right? We're given an acceleration. We know we have a relationship between our angular acceleration and our regular acceleration. So if we move into the angular space first, and then start working to velocity and displacement from there, that's probably going to be our best bet. So we know, as we just went over a lot, we went over a lot of equations and a lot of relationships. But the first thing I'm going to do is just move into the angular. So I know that I've got a relationship AT equals alpha times r. Right? Angular acceleration times the radius of this thing that's rotating. So I can substitute in my 4t. 4t equals alpha times r, and I know that r is 0.2. So if I divide that over, I can get a relationship for my angular acceleration of 20 times t. And that's going to be in radians per second squared. We're going to assume that that is going in the positive direction, which here we have as clockwise. So we've got a really good start, right? Now we're in our angular zone, and we can work through some of those relationships that we know we have between angular acceleration, angular velocity, and angular position. Because we know our angular acceleration is the derivative of angular velocity with respect to time. And we know our angular velocity is going to be the derivative of our angular position with respect to time. So with that in mind, we can take this relationship here and rearrange that a little bit. So I'm going to say that alpha dt equals dw. And then I can integrate that for any given time. So I'm going to start at time 0 and go to time t. So that'll give me this integral for any arbitrary time equals alpha. And we know alpha is 20t dt equals my integral, and it did say we're starting from rest, so I'm going to have my initial angular velocity be 0 to my final angular velocity, which is the thing we're trying to find, d omega. So that when I do this integral, I'm going to get 10t squared evaluated from 0 to t equals omega. So my omega in terms of time is just going to be 10t squared radians per second clockwise. These dimensional arrows can be really helpful indicating clockwise, counterclockwise. You can also write it out. You can say clockwise, or if you like writing the whole word out for clockwise, you can indicate it either way. But it's typical to kind of indicate direction for those angular velocities and angular accelerations, even if you have a positive convention. And so that was our first part. Now our second part was to find that angular position, and we can do that by integrating. And I'm actually going to do that over here. If I rearrange this so that I get d theta equals omega dt, integrate, it told us, if I pop back up here, that our initial theta was 0. So from 0 to theta, d theta equals the integral from 0 to t, get it in a function of time, of omega, which was 10t squared, dt. And so when I integrate this, I get theta equals 10t cubed over 3 from 0 to t. That's going to give me theta is just 10t cubed over 3 radians. So both of them kept their t's in their equations so that we can get these in terms of time. Right, we were finding that angular position and angular velocity in terms of time. So having these relationships within the angular acceleration and position and velocity themselves are helpful, but it's really, really helpful when you can swap back and forth between your linear accelerations, velocities, positions to your angular velocities, positions, accelerations, and vice versa, right? The swapping between them is what a lot of these initial kind of rotation about an axis kinematics problems, what you're going to be learning to do. You're going to be swapping between those a lot. So that later, when we get to our kinetics, you'll be really familiar with that, and it'll be a little bit easier to apply our kinetics, like force and acceleration, all of those things. Let's take a look at another example, now kind of working in the opposite direction. So in this example, we have a disk that is rotating with an angular acceleration of alpha equals 3t squared plus 12 radians per second squared, where t is in seconds. If the disk is originally rotating at omega equals 12 radians per second, determine the magnitude of the velocity and the n and t components of acceleration of point A at the instant that t equals 0.5. And I realize point A is not on my drawing, but it's right here. So looking at what we're given in this one, now instead of trying to find our angular velocities and positions, we're trying to find our linear velocity and the normal and tangential components of our acceleration. So let's take a look at everything we're given. We're just going to write it out. Our angular acceleration, they gave us alpha is 3t squared plus 12. And that was in radians per second. And then our initial angular velocity is 12 radians per second. and we want to find the magnitude of the velocity. So what is velocity? And the normal and tangential components of acceleration, all when t is 0.5 seconds. So we're going to go ahead and assume that our rotation is just the way that it's indicated as counterclockwise on our disk over here. And let's go ahead and see what we can piece together to figure out what our velocity and our normal and tangential accelerations are. So again, probably a good place to start would be writing down some equations that we know can relate these things together. So we know, for example, that our tangential acceleration is going to be alpha times r, and we know our normal acceleration is omega squared times r, and then we also know our velocity is omega times r. So we can use any combination of these to see where we can get going in solving for our accelerations and velocities. I'm going to start with our tangential acceleration. That one seems to kind of make the most sense to me personally. You can solve this in all kinds of different ways. You can do whatever approach you think is best. You can start with velocity if you want to. For me, this one just seems like it's the most obvious because I'm given this alpha, and it's the only thing I have here that deals with the alpha at all. So to me, that's where I would start, even though it was technically the last thing asked for over here. So our tangential acceleration is alpha 3t squared plus 12 times the radius, and that radius over there is 0.8, which I guess we could add into our list of knowns that r is 0.8 meters. And so now remember, we're finding this at time t equals 0.5, so I can just go ahead and plug in that t here. I don't need to do anything to it, I can just plug it right in to get my tangential acceleration is 3 times 0.5 squared plus 12. And then all of that is times 0.8, which when I punch that into my calculator, I'm getting 10.2 meters per second squared for my tangential acceleration of point A. Now we don't really know where point A is at that 0.5 seconds. We didn't really calculate that, so it's a little bit difficult to give it a direction. So we will just leave it and say it's in the, it's in the direction of rotation. We don't need to necessarily indicate a direction on that. So next, if I look at both of these relationships over here for my normal acceleration and for my velocity, they both need omega. And that omega is that omega at 0.5 seconds, right? It's that angular velocity when we're at our 0.5 seconds. So I'm going to need to find that. And luckily we've got another relationship that we have between our angular acceleration and our angular velocity, and that's that our angular velocity, take the derivative of that with respect to time, we can get our angular acceleration. So if I rearrange this, alpha dt equals d omega, and take that integral, I can get this relationship for omega. I can find what that angular velocity is. So the integral for my times for alpha from 0 to 0.5. And then my alpha, remember, don't use this value that we just solved for. We don't want to use that. We want to use the equation they gave us. 3t squared plus 12. 3t squared plus 12 dt equals integral from our initial omega, which they gave us was 12 radians per second. So 12 2 omega, d omega. So when I do this integral, I'm going to get t cubed plus 12t, evaluated from 0 to 0.5, equals omega minus 12. Right, the integral of d omega is just omega. Evaluated from 12 to omega is omega minus 12. So here I'm going to get 0.5 cubed plus 12 times 0.5 plus 12 from this 12 on the right side to get that omega value. So the angular velocity at 0.5 seconds is 18.125 radians per second. So this guy is super handy, right? Now that we have this, we can use him in both of these relationships up here for our normal acceleration and for our velocity. So let's go ahead and use, it doesn't matter which one you do first. You can do the velocity if you want to. You can do the normal acceleration. I'll do velocity here. So my velocity is omega times r. Velocity is omega times r. That one's really simple. 18.125 times my radius was 0.8 means that my velocity is 14.5 meters per second. And then the last one I need, that normal acceleration. That normal acceleration an equals omega squared times r. Omega squared, 18.125 squared times the radius of 0.8 gives us a normal acceleration of, it's a huge number, 262.8 meters per second squared. A huge amount of normal acceleration due to this angular acceleration increasing in a quadratic with time. So here we were able to use that angular acceleration, angular velocity to find our linear velocity and normal and tangential components of our acceleration, just using these relationships that we've learned. Alright, I've got one last problem for us to look at together today, but I'd really like for you to try to do this one on your own before we work through it together. See if you can piece together these concepts, understand what we're doing, see if you can attempt this problem on your own without any help first, and then we'll go through it together. So this problem says that a wheel has an angular velocity of 10 revolutions per second and a constant angular acceleration of 3 radians per second squared. Determine the number of revolutions required for the wheel to have an angular velocity of 20 revolutions per second. What is the time required? So there's no diagram for this one, it's just a word problem. But go ahead and pause the video here, see if you can work through it on your own, and then we'll talk about it together. Alright, so let's take a look at this problem and how we can approach a problem like this. So we have no diagram, not that we necessarily need one, but if you want one, we can draw a wheel that is spinning. That's really about all that they had given us in this problem. A wheel has an initial angular velocity. So that's going to be our omega naught, of 10 revolutions per second. Now, this may have tripped you up if you didn't clock that this was a revolution and not a radian. So you're going to have to convert this angular velocity into radians per second from our revolutions per second for anything to work in this problem. So to do that, we can just multiply by 2 pi. That converts us from radians, or from revolutions to radians. So 2 pi radians is 1 revolution, which means that our initial angular velocity is actually 20 pi radians per second. And then we have a constant angular acceleration of 3 radians per second squared. So this was the other big, super important flag for you in this problem. Constant angular acceleration. So with our constant angular acceleration of 3 radians per second squared, note our units are actually correct in that one. With that, we know we've got constant angular acceleration. We can use those constant angular acceleration equations, right? The omega equals omega naught plus alpha t, all of those equations. We can use those for this constant acceleration problem. Let's see, let's pick out the rest of the information. So we want to find the number of revolutions required for the wheel to have an angular velocity of 20 revolutions per second. So when our angular velocity is 20 revolutions per second, note again it's revolutions, so we'll convert that as well by multiplying by 2 pi. That gives us 40 pi radians per second. We want to know what the number of revolutions is. So we're finding number of revolutions for that angular velocity. And we also want to find the time. So 2 things we're looking for: time required and number of revolutions. Now, I'm going to go ahead and start with the time required. It's probably a little bit more straightforward, and if you may have noticed, I actually already wrote a really handy equation down for this one. So let's go ahead and find that time required, and then we'll deal with that number of revolutions. So again, since this is constant acceleration, I can use my constant acceleration relationships to solve this problem, rather than going through integrations or anything like that. You can do it that way, and it's acceptable if you did do it that way and you got your answers to work out. That is 100% okay. You can get there through integration, no problem. But sometimes it's nice to just have an equation to plug things into, which is what I'm going to do here. So for my time, if I rearrange this, I'm going to get omega minus omega naught all over angular acceleration. Right, just rearranging that equation that I wrote. Because I have all of these things already. I have what my final velocity, my final angular velocity is. That's 40 pi radians per second. I have my initial angular velocity. That was 20 pi radians per second. See, I almost wrote 10 there, and that would have been bad because my units would not have matched at all. It's 20 pi radians per second, all over that angular acceleration they gave us of just 3. So when I punch that into a calculator, it's going to give me a time of 20.9 seconds. 20.9 seconds, that's the time required to go from an angular velocity of 10 revolutions per second to an angular velocity of 20 revolutions per second. Now we're going to deal with this number of revolutions thing. Number of revolutions it has to go through to get an angular velocity of 20 revolutions per second. So again, I'm still undergoing that constant acceleration, so I'm still going to probably want to use those constant acceleration relationships. The difference here is just knowing how to find that number of revolutions. And because we have that relationship of 1 revolution is 2 pi radians, what we can do is find how many radians it has gone through and then convert back to revolutions. And thankfully, in those constant angular acceleration equations, we have a relationship for that. You can use either one you want. There's 2 you can use, whether you want to use omega squared equals omega naught squared plus 2 times alpha times theta minus theta naught, Or if you want to use that theta equals theta naught plus omega naught times t plus 1/2 alpha t squared, since we have a time, you could use this one as well. I'm going to use this first one, but it truly does not matter. You could use either of them, where the thing we're solving for is going to be this guy, right? This difference in that angular position. That's going to tell us how many radians we've traveled through, and that's what's going to give us our revolutions, converting out of those radians into revolutions. So for this, if I go ahead and rearrange this to solve for my theta minus theta naught, right? This change in radians, where my initial, I'm going to assume my initial position is just 0. If I rearrange this, I'm going to get omega squared minus omega naught squared all over 2 times alpha. And again, I have all of those values. And this is again where it's really important that I have that converted from those radians, or from those revolutions into radians, because I'm going to be squaring these. So 40 pi, all of that squared, minus 20 pi, all of that squared, divided by 2 times our angular acceleration, which was 3. And when I punch that into my calculator, it gives me 1973.9 radians. So that's how many radians it's going through to reach that new angular velocity. And to find what that is in revolutions, I can just divide this by 2 pi. There are 2 pi radians in a revolution, which gives me that we need about 314, or if you want to round up to the nearest whole number, that's fine too. 314 revolutions to go from our initial angular velocity of 10 revolutions per second to our angular velocity of 20 revolutions per second. We'll have to go through 314 revolutions in 20.9 seconds.